So last time that you rode a bike, how much did you think about the machine that you were riding? Bicycles are amazing machines. When else can you ride a human-propelled, hyper-efficient machine stabilized by twin gyroscopes? They're also a pretty cool way to learn about the motion of machines. So my name is Dan Baker, and I teach engineering at Colorado State University. I love bikes. I love to ride them. I love to work on them. And I'm really excited here to do this lecture today for the kids who are in charge. So as we think about bikes, one thing you can think about bikes is that how efficient bikes are. Okay, so bikes only use about, or bikes would get about 1,600 miles per equivalent gallon of gas. That's about 640 kilometers per liter of petrol. So that's super, super efficient, like more than 100 times as efficient as most of your cars. And so as we think about bikes, we can think about their efficiency. We can think about, in a lot of ways, their mechanical simplicity. They're actually one of the best things if you wanted to start working on mechanical things. A lot of the different mechanical systems are kind of repeated with the bearings and the different pieces. So they're just a really cool way to learn about engineering. So as we think about engineering, a definition of engineering could be taking scientific understanding of the natural world and using it to invent, design, and build things to solve problems. Okay, so in my classes that I teach, I have a bunch of different types of engineers. I'm actually a civil engineer, and civil engineers, we create roads and bridges and water systems. And a lot of my studying has been in looking at how we can better engineer streams and rivers so that
My cousin's a civil engineer.
well, that's awesome. What kind of civil engineering do they do? Do you know?
I think he's leaning more towards roads.
Awesome.
Or bridges. I'm not sure which.
Yeah, there's a lot of
We
great
haven't
work.
talked to him for a long time.
Well, you'll have to check with him now, and you'll have to say, hey, what kind of civil engineering are you going to be doing? And there's like a general civil engineering degree, and then people can go out and work in a lot of different fields. There's also mechanical engineering, and so it's actually mechanical engineers that tend to design bicycles. They design cars and kind of just mechanical working systems. I also teach environmental engineers, and environmental engineers help clean our water before it comes out of your tap. They also clean the water once it leaves your house and take care of a lot of other environmental challenges. I also teach biomedical engineers, and biomedical engineers make a lot of different basically mechanical systems that interface with the human body. So they could make, say, artificial heart valves and prosthetic limbs and some of these different things. So I have a lot of different students taking my classes so they can go forth and do a lot of these different areas of engineering. So the two classes, sorry about that. The two classes that I teach, one's called statics. And in statics, nothing actually moves. And so I thought for you guys today, instead of talking about nothing that moved, would go toward the other class that I teach, which students take after statics. It's called dynamics. And in dynamics, everything moves. And with everything moving, we have a couple of different topics we talk about. And I'm actually going to share with you today an introduction to the hardest topic that my sophomore and junior level college engineers learn. But I know that you guys can do this, and it's called rigid body motion. Okay, so as we talk about what is a rigid body is something you cannot break, you cannot bend, you cannot destroy. And I know kids are really good at doing those three things. But we're talking about things that we're not worried yet about what kind of material something has to be built out of. At this point, we just want to figure out what's the motion it will be going under, what are the kind of forces they're going to be applied to that body. And this idea of motion comes before relating motion to forces. There's a later topic we call kinetics, and kinetics relates forces to motion. But right now, we're just going to talk about motion. And the cool thing is we're going to relate all of this to bikes. And so next time you get on your bike, you can look at your bike and be like, hey, this is doing that thing that we learned about the other day. So rigid body motion. All right, so I need to spend a couple slides here giving us some introductory information just so we're all kind of on the same page. There's gonna be two different kinds of vectors that we talk about, both linear and rotational. Okay, so a vector is made up, sorry about that there. So a vector is made up of a magnitude plus a direction. Okay, so a magnitude is just going to be a number of something. Okay, so like the number of bowls of cereal you ate this morning, how many siblings you have, what the street number of on your house is. Like I live at 225. So those are all just magnitudes. But the special thing about vectors is their direction. And so we add a direction to a magnitude, we end up with a vector. And so if you ride your bike to your friend's house and they live to the east of your house, you could ride your bike at 10 miles per hour straight east. Or you can push downward on your bike pedal with the half of your weight if you have both feet on the pedals, right? So a magnitude plus a direction makes up a vector. Now, the types of vectors we're going to talk about today, these linear vectors, are going to be positions. So position, you can think about that's really just like a length, how far something is, and a velocity. And if you guys have questions as you go, feel free. That was great. Milo had the question there. Feel free to ask me questions as we roll along, because I want to make sure that I'm not using words that you haven't heard before and whatever else. So feel free to jump in. Now, positions and velocities are actually related. And they're related by a really cool math thing called a derivative. Now, derivatives are actually taught in college level math. So I'm going to teach you a very simple derivative today. And it turns out that velocity is the time rate of change of the position. Okay, so let's say that you're on your bike and you travel 0.5 kilometers and it takes you 20 minutes to cover that distance. Okay, so we talked about a time rate of change. So we're talking about a position, a length, divided by a time. So it's also a fraction. So if we wanted to convert this into kilometers per hour, we can multiply this times 60 minutes divided by 1 hour. And this kind of unit conversion is a really important thing we do a lot in engineering and all different kinds of STEM classes. And really we just set this up so we could cancel the minute here with the minute here, get rid of those minutes. And we're left, let's see here, half, which is 0.5 times 60, that's gonna give me 30. 30 divided by 20 is gonna be 1.5. Okay, so 1.5 kilometers per hour. And so what we just did is we just turned this length change, a half a kilometer, into a velocity by taking a derivative. The time rate of change of the position is the velocity. Okay, so you guys just did a derivative, or I did, and hopefully you learned along with me. Now the direction, we talked about northeast, southwest. So let's go ahead and list that on here. Compass rose could give us direction. So north, east, west, and south. That could give us direction. The axis system that we're going to use today, we'll use what's called a Cartesian axis system. So a Cartesian axis system is based upon typically a horizontal X and a vertical Y. Okay, so you can think about those being in the plane of your screen that you're looking at. And there's actually a third dimension, since we do live in a three-dimensional world, that's coming out of the screen toward you. We call the Z-axis. Okay, so the X, Y, and Z axis system. And so we'll reference those a little bit, not too much, but just to note that that's how we come up with both a magnitude and also a direction. So as we're talking about position, we'll be talking about position vectors, say today in meters or kilometers, and velocities in things like meters per second or kilometers per second. I tend to use square brackets for my units. All right, so those are the linear vectors. Those should be all fairly familiar to you. You've seen the, the velocity your parents' car is traveling and measured things at school and whatever else. The other kind of vectors we're going to talk about today are rotational vectors. And these might be a little more new to you. Now we're still going to talk about position and velocity, but we're going to talk about angular position and angular velocity. All right, so angular position, we use a lot of Greek letters for our symbols, and so we tend to use the angle theta for angular position, and we use a curvy kind of a loopy W called omega for our angular velocity. Sorry, this pen's kind of shooting up on me there. So theta and omega, these are also related by that same derivative. And we won't go through another derivative for these, but there's a lot of parallels between linear motion and angular motion. And so just kind of drawing those parallels. And so as we think about the direction of these angular velocity vectors, I want everybody to hold up your right hand and make a thumbs up sign, just like you see in the picture. Okay, so the direction of your fingertips as they wrap around your four fingers they're all together is basically the direction of rotation. And so the axes around which your fingertips are rotating is your thumb. And we use what's called the right hand rule to say that anything going upwards or out of the page, we tend to call positive, and anything going downwards or out of the page, we call negative. Okay, so even if you point your thumb at your face and take a look at it there and see your fingers wrapping around, you can see that's a counterclockwise direction. Now you can get really flexible and point your thumb away from your face and see that's going to be a clockwise direction, right? Using your right hand. It's actually really fun to give exams in my classes because I know students are actually working and learning and moving forward because they're all using their hands to do this right hand rule. We have multiple different things that people have to do with this right hand rule. Okay, so to give you an opportunity to practice this right hand rule, I am going to start the rotation of this wheel, and I want you to tell me if it is positive or negative rotation from the right hand rule. Now, noting here that your thumb is either going to go into the page, or excuse me, not page here, but the screen, into the screen or out of the screen. Okay, so let me start this. Who knows what direction that rotation was going in?
Counterclockwise.
It was actually going, so let's look at it again. Is that clockwise or counterclockwise?
Wait, it looks like it's going clockwise.
Clockwise, that's correct. And so with the right hand rule, do we call clockwise positive or negative? Using your fingertips, so wrap your fingertips around in the direction the wheel's rolling around. Your thumb should go into the screen, and we call that a negative angular velocity omega. Okay, so we could also say it's something like the negative z direction. If like our positive z is coming toward us, that negative z axis is going away from us. Okay, so that's how we use the right-hand rule. Now, that's a tricky thing to do. If you didn't latch onto that right away, I have students that have had me for a full year, and they're still like, now I think I understand this right-hand rule, but let me work on it. And they're like 20. So don't worry if you haven't mastered that yet. All right, so that's the idea of the right-hand rule. Now, some other interesting things about rotational vectors, and especially as we talk about angular velocity, we tend to use a unit for angular velocity called radians per second. Now, this is a similar unit, but is just a different expression that if you've ever looked at the dashboard of your parents' car and you see RPM, that's actually revolutions per minute. And that's the revolutions per minute of their motor. So this would be a bit different of a measurement, but still an angular velocity of this wheel. Now, have any of you talked about radians yet in class? Learned about radians versus degrees?
No.
Okay. Well, I'm going to teach you a little bit about that. Radians are really cool. They're my favorite unit because I call them the ghost unit. They always just disappear. But there are 360 degrees in one circle, right? All the way around. It turns out that there are 2 times pi radians in a full circle. And so it's just a different way of measuring the distance around that circle. Now, I know probably many of you will know that the circumference of a circle is equal to what? Anybody remember that equation? Had some geometry? 2 pi r. So it turns out that this 2 pi is the amount of angle, if we call that angle, say theta, all the way around a circle, times its radius gives you the circumference. And so you could also use the same information if you wanted to. Say that you wanted to find the length of your bike tire, just 1/4 of its length. Okay, so from here to here, we call this some distance, call it S. And so if we measured our angle here to here, we call that theta. Now this theta for 1/4 of the wheel is going to be theta is equal to pi divided by 2, right? 1/4 of 2 pi. And then we can just multiply that times the radius. And so if you had a giant bike wheel, say it was 1 meter in radius, which would be 2 meters all the way across, you'd end up with pi over 2 as your distance. And so of course pi is 3.14, and so a distance of about say 1.5 meters would be the 1/4 of this bike tire. All right, so we talked about linear vectors and rotational vectors. Now we're ready to talk about motion. Okay, so the simplest kind of motion, the one we think about probably most classically with motion, is translation. Okay, so translation are when things simply move in a straight line. And so, of course, if this bike was riding across, I didn't even show the motion of the wheels because I wanted to think about just linear motion, nothing rotating at all. And so one of the parts that's on your bike that is in pure translation is your bike frame. Okay, and so your bike frame, once you learn about, say, the velocity of the crank down here, so say we find the velocity of your crank, it turns out that the velocity of your seat is going to be exactly equal to the velocity of your crank. Okay, so these are vectors. We talked about that vectors are made up of magnitudes and also directions. The exact same magnitude, the exact same direction for things that are in translation. And so computing motion with translation is fairly straightforward. If you learn about the motion of one part, you know exactly about the motion of every other part in that system. Now, getting into rotation gets a little bit more complicated. Okay, so we're going to look first at what I'm going to call pure rotation. So this pure rotation is going to rotate around the center of this wheel. Okay, so not like your bike rolling down the street, but like your bike if you flip it upside down, you need to change your flat tire or something like that. And so here you're going to get to practice your right-hand rule again. And so now this wheel is rotating counterclockwise, wrapping your fingertips in the direction of that motion. Does anybody remember, is that positive or negative from that right-hand rule that we talked about with your thumbs up? All right, that's positive for our right-hand rule. Hopefully all of you that were muted back there are like, yeah, I got it, thumbs up, we got it. All right, so positive omega. Now what we're gonna do is we're gonna relate our linear velocity to our angular velocity. Okay, so linear, we're gonna use V. And then our angular, we use that curve EW. And then we're gonna use a distance R. And this distance is gonna be away from the middle point right here. Okay, so if we're looking at the linear velocity of that middle point, it turns out that if your bike is sitting upside down, the velocity of that center is going to be the velocity of the bike that's sitting there on the ground. We're going to find a linear velocity equal to 0. But it's pretty obvious that one edge of your bike tire, say this point up here, is not going to have a velocity of 0. It's going to have a velocity moving to the left. And also this point on the bottom here is going to have a velocity moving to the right. And so we could show the motion here one more time. So as that wheel rotates around, the middle has a 0 linear velocity. The top edge and the bottom edge both have actually equal and opposite linear velocities. Now, another really cool thing that we could do is not only find the velocity of these 2 points, but I can actually draw something we call similar triangles. Now, let me match the length of these vectors so this looks a little bit better. This should be equal top and bottom. And I can draw with straight lines from tail to tail on the vectors and from tip to tip on the vectors. And I come up with this distribution of velocities. And so if you wanted to find the velocity of, say, halfway between your center hub and the outer edge, it turns out it's going to be half of the velocity at this top edge, right? And you could do that with any distance away from that center. Essentially, it's all based upon this equation right here. Linear velocity equals angular velocity times distance away from our point of rotation. All right, so that's pure rotation. Of course, that isn't yet how bike wheels move, right? Because bike wheels are traveling down the road. Your center hub is not stationary. It's actually moving with you. And so it turns out for what we call general motion that we are going to combine translation plus rotation. Okay, so translation plus rotation equals general motion. And so general motion looks like this. Here's the bike wheel rolling down the road. I'll just roll back and forth here a few times. And so in order to find the motion of this wheel in general motion, we can actually combine, like I said, that translation plus rotation, and I'll bring in an overall image here of the bike. And so if the bike is going in this direction, so here's our velocity of the bike. And let me go ahead, and this is the absolute velocity of the bike. We'll say that here's also the velocity of the bike, and down here at the road surface, another vector, all velocity of the bike. Okay, so this would be true if you were skidding your bike, right? You had your wheels all locked up, that every point on your frame and on your wheels would all have exactly the same velocity. But we know if this wheel is rolling down the street, that it is additionally going to have some rotation going on of that front wheel. Okay, and the rotation direction would be in this direction here. This is positive omega, right? Wrap your fingers in the direction of that arrow tip and your thumb should come toward you, coming out of the screen. And so if that's my omega, we find out that the relative velocity. Now I'm going to talk about this idea of relative and absolute. Absolute means measured compared to the earth. Okay, so if you're walking down the sidewalk, you have an absolute velocity of however fast you're walking. Now, if you're walking down the sidewalk and your friend is walking in the opposite direction down the sidewalk, you have a relative velocity between your two bodies, right? Your two bodies that are both moving. And it will turn out if you're both walking in the same velocity, but as they're walking toward you, it feels like they're walking twice as fast toward you relative to your movement, even though in an absolute context, they're only walking the same speed that you are. Okay, so that's this idea of relative. So the wheel relative to the bike ends up having a 0, so we'll use a V sub REL, velocity relative, equal to 0. So this is basically coming back to that fixed axis, that pure rotation we talked about in the previous slide. So the top of the wheel, given our omega that's positive from the right-hand rule, is going to the left relative to the middle. The bottom of it is going to the right. And so when we look for the absolute velocity of this bike wheel, we need to add together these two vectors and then add together these two vectors. So what we find is that the top of the wheel is moving, pen back, is moving at 2 times VB. I'll just put 2 VB, twice as fast as the bike is moving. But down here at the bottom, we find that this is going to be equal to 0. So I just told you, which is kind of wild, that on a moving bike, there's a point of 0 velocity that is not moving at all. And that point ends up being down here, this contact point with the road. And so we call these points down here, we call them centers of 0 velocity. And it turns out that these centers of 0 velocity are super, super helpful for us to solve for motion of very complicated systems, because we can actually treat those points just like they're a fixed axis point, just like when we had the bike flipped upside down, we looked at pure rotation. If you remember that we drew that, that triangle of all of our velocities, we draw that same triangle here. Let me pick a different color. We'll go with orange. And so if we have 0 velocity at the bottom, and we draw this tip-to-tip and tail-to-tail vector, we just found that we created a distribution of velocities along the center line of this wheel for both the middle. I didn't quite get that drawn to scale. It should have been right inside the triangle line there, and also the top, and any other point here in between. Okay, so that's this idea of centers of 0 velocity. Now, something else to point out is that your omega is actually going to be constant for the entire wheel. Okay, so it doesn't matter what point you pick on this wheel, it'll all have the same angular velocity, but linear velocity varies by location. Let me put that into words. So here we can say that linear velocity varies with location. So linear velocity is our V, and our angular velocity which is our loopy W, or omega, is constant on a whole body. Let's put a whole wheel, since we're talking about wheels. All right, so linear velocity varies with location. It turns out it not only varies by magnitude, it also varies by direction. But our angular velocity is constant, so it stays the same. All right, so the last topic we're going to talk about are gear ratios. Okay, so for any of you that have geared bikes, and I'm guessing you're probably getting into geared bikes, my daughter who is
It's a gear bike.
Awesome, awesome. So this should help you think about how those gears work. And as you're shifting between gears, what direction you want to be shifting. All right, so let's start with a 1-to-1 ratio. Now let me just show you how this all works, just so we can kind of see. It's obviously the lower half of a person. We have orange legs. There's a crank, there's a front wheel, there's a back wheel. And so this would be like a stationary bike or a bike on a stand, but it gives us an opportunity to look at these gear ratios. So if your gear size in the front and your gear size in the back are exactly the same size, we have a 1-to-1 ratio of those gears, not only is the linear velocity of your chain, right, because your chain is hooked to the front, your chain is hooked to the back, so your linear velocity is going to be the same, but also your angular velocity is going to be the same. One revolution of your crank means one revolution of your wheel. Now, if you want to change your speed a little bit, you can shift. And so let's say that we shift to a larger chain ring in the front. So any of you with geared bikes, is this going to make you go faster or slower? And you can just guess. Say that again.
Slower.
A little slower. Yeah. So for one thing, it's going to make pedaling harder. But it actually, if you can get up to the same angular velocity you had before,
Will make you go faster.
It'll make you go faster. That's right. So we can see here that I'll do one revolution of the crank. Oh, that back wheel's rolling right along. So a half revolution of the crank was a full revolution of the back wheel, and then another half revolution brings you to 2 revolutions. So it's basically 2 revolutions of the back wheel to 1 revolution of the front. Now we could go the other direction too. Say you needed to climb a really steep hill, or you also see this used if you have a really low torque but high speed motor that you're powering something with, but you don't want things to turn very fast. Let's go all the way up to a 4-to-1. Okay, so here we're gonna make 1 crank of our legs, 2 cranks of our legs, 3 cranks of our legs, 4 cranks of our legs, and we've only made 1 revolution of our back wheel. Okay, so this would make it very easy, but your top speed would be very, very slow. And so not a very, it just depends what your goal is, right? If you're climbing a really steep hill with a heavy load, that might work fine. But if you want very much speed, you're not gonna get very much speed out of that. Okay, so really what we're doing there, we're varying the radius, the distance between these centers of rotation and the gears. And by doing that, we're also varying their angular velocity, right? Still gonna be at the same linear velocity here of the chain, contacting this point as contacting this point, because it's the same chain. The chain can't stretch or compress or anything else. And so the same linear velocity of the chain, changing radius gives us a different angular velocity. So if you're pedaling along and you want to go faster, you tend to want to go bigger in the front and smaller in the back. And if you wanted to make it a little bit easier and go a little slower, you want to go smaller in the front and bigger in the back. And then you have to dial that in to, if you have numbers on your bike, figure out which number goes in which direction. But that's how we can relate motion and this motion of rigid bodies to bicycle gears as well.
Yes.
Go ahead.
I have a question. What happens if the fractions 1-to-1 or 2-to-2 or 3-to-3 or 4-to-4? Does it make a difference?
That's a great question. It turns out it does not make a difference. If you pick the same size in the front and the back, you're still going to get the same angular velocity, which means you'll have the exact same kind of gearing ratio. Even if I went like 4, this is going to look really funny, 4-to-4, we're still going to get 1 revolution in the front to 1 revolution in the back.
Okay.
Great question. And I'm going to share the link to this, and I've actually got a number of other kind of experiment things that you guys could do on your bikes. I'll share those that you can hopefully get posted below the video as well, so that you can play with some of these things on your own bikes to see what happens. Other questions here on the gear ratios? All right, so today you have learned about linear and rotational vectors. You learned about their axes systems, you took a derivative, some really cool math. You learned about the right-hand rule, which the right-hand rule is just a sign convention that we can use. So when we talk to other engineers, we're kind of talking the same language. We learned about translation and rotation, and how both translation and rotation are included in general motion. We also talked about gear ratios. Okay, so a lot of really cool bike-related stuff that is all based upon rigid body motion, which, like I said, is this topic we teach in dynamics. And so I'm happy to open it up to any other questions you guys have at this point. Let me put it over to video so you can see my face. Let's see if I close this. Other questions I can answer for you today? You guys look like my students after a full semester of like online learning.
It is Friday.
I hear you. I hear you.
But that was super cool. That was yeah, until now I never really processed how much goes into the movement of a bicycle. Oh my goodness.
There is a lot. There's a lot that goes into not only the building of it, just as a mechanical system, but the coordination for your brain to figure out how all these systems interact. They always joke about, oh, it's easy. It's like riding a bike, and riding a bike is actually a pretty complicated mental and coordination things. You're doing separate things with your legs than you're doing with your arms and your. Like I said, the bike is kind of doing its own thing. So like I said, I'll send you some links that the kids can do on their own bikes, some videos and some different things they can experiment with to both see a few of these things that I talked about today, as well as some other topics, mainly to deal with that the bike is a gyroscope. Basically, each wheel is a gyroscope. And that's really cool to think about, that a bike self-stabilizes itself once you are riding it.
If you have stuff to send to the class, you'll have to send it to me and then I'll pass it on to them.
Perfect. Perfect.
Yeah.
Yeah, I'll just send it. Let's see, I had, I think Vicky's email. So yeah, or you can send me an email, or I'll figure out, I'll get it to you guys and you can figure out where.
Yeah, you can send it to Vicky as well.
Okay.
Yeah, cool.
Perfect.
Last chance for any questions. Okay, well, thank you so much.
You're welcome. Awesome. Yeah, thank you guys.
Thank
You're welcome. I hope you get out on your bikes and look at your bikes a little bit differently. Start looking at your bike like an engineer instead of just a kid on a bike.
Bye. I'm actually supposed to be going for a bike ride very soon, like in 10 minutes.
That's perfect.
For me, in like an hour.
Oh, perfect. Because the best way you can learn things, right, is to teach people, right? So you can teach whoever you're going on your bike with all the cool things you learned today.
Very true.
Okay. Bye.
Thanks.
All right, bye-bye.
Bye.
All right, thank you.